Undetermined coefficients in the first ODE course. I always had difficulty in my intro ODE courses explaining to students what particular solution template to use in the method of undetermined coefficients. So in this webinar, I'll show a few things I tried that I judged to be unsuccessful. Then I will describe the approach that I learned as an undergraduate studying out of Rainville's elementary differential equations text. And then I will show how I implemented that approach using Maple. So, as you, I'm sure, can recall, a particular solution for a linear, non-homogeneous ODE can always be found by variation of parameters, provided the appropriate integrations can be carried out for certain non-homogeneous equations, constant coefficients, where R of x, the right-hand side, is itself a fragment of the general solution of the differential equation gr equals 0. So this g is an annihilator of that right-hand side. Method of undetermined coefficients is computationally way less intensive than variation parameters. And really, once you get the appropriate template for the particular solution, the just routine algebra finishes the task and you don't need to do any integrations. The challenge that I always found is extracting from that R of x, that right hand side, what differential operator G will annihilate R. And then you need to get the complete form of the general solution to that equation, gr equals 0, for which R of x might be but just a fragment. So this requires recognizing what the roots of the appropriate characteristic equation for g of r equals 0 might be, and it requires a reverse thinking requirement that, in my experience, students don't have enough time to master. So if they had enough time to go from forward progress through the process to see the key to thinking backwards, it would be okay. But generally, you spend one day on this, and it's just not enough time to make this transparent. So let's take a look at the things that I've tried without great success, and then we'll see what approach I would really have liked to teach the students, and then to see what tools Maple has to make that approach viable. So let's take a look at some of the things that I tried, but I didn't think were really tremendously successful. So I tried a couple of approaches here. And I would tell the students variation parameters always applies, but then you're going to have these integrations. Undetermined coefficients sometimes applies, and when it does, it's easier to do. So it works for linear ODEs with constant coefficients. You've got to look at the driving term, and you've got to visualize it as a linear combination of terms that are themselves pieces of solutions of linear ODEs with constant coefficients. And that should be enough for them to understand, if they truly understood what a linear ODE with constant coefficients generated. So the terms in R have to be obtainable from the exponential guess. And that includes terms that arise from repeated roots. So that's the recipe. If students could grasp that immediately. So then I said, okay, they need more instruction. So I said, okay, I'm going to make table 1, which is a bunch of examples. If the root lambda shows up in a solution to a linear constant coefficient ODE, lambda equals 0, you can e to the 0 t. That's 1. So if you just have a number, 2, 3, 4, 5, that means lambda equals 0 was a root. And if lambda equals 0 has multiplicity 2, then you're going to have an addition to a 1 or constant t, e to the 0 t, which is t. And if it has multiplicity 3, so you have lambda equals 0, 0, 0, you're going to have a t squared e to the 0 t, or you're going to have a term just t squared. But what if lambda is a non-zero constant, real constant, like 3? Then you're going to have a term e to the 3t. And if you have multiplicity 2, so it's 3 comma 3, you'll have a t e to the 3t. And if multiplicity is 3, you'll get a t squared e to the 3t. If you have an imaginary number like plus or minus 3i, then you will get the possibility of two terms, cosine 3t and sine 3t. And if this pair of roots shows up with multiplicity 2, you're going to have a t e to the plus or minus 3 it, in which case you're going to have a t cos 3t, t sine 3t. And if the multiplicity is 3, so that really you've got 6 numbers here to deal with, you have a t squared times the cosine or the sine. And if you have a full complex number like 2 plus 3i, then you will have solutions of the form e to the 2t cos 3t, e to the 2t sine 3t, and multiplicity 2, you'll have a t out front of that, so you get a t here and a t here. And if multiplicity is 3, you're going to get a t squared. So you have a t squared e to the 2t cos and t squared e to the 2t sine. And then I would go through that song and the dance here explained, trying to get students to visualize what happens when you go from root to term, so that they can look at term and go backwards to root. That is the hard part that I found. So to this, I eventually decided to add table 2. In table 2, I introduced this term, latent roots. These are the roots that are hiding in that right-hand side. And so I created another bunch of examples. I said, if your right-hand side should look like this, you would see this term e to the 3t, and you'd say, oh, there was a root lambda equals 3 in the characteristic polynomial for the operator g that annihilates the right-hand side. And if you had a cosine 5t, then you had roots plus or minus 5i, in which case the guess for the template there for the particular solution would be a multiple of e to the 3t, a multiple of cosine 5t, and a multiple of sine 5t. And I would drag the student through these 10 examples. If you see a right-hand side that says minus 3 minus 4 sine 5t, this minus 3 tells you you had a root of 0, and the 5t here says you had a plus or minus or plus and minus 5i. And so the guess for the template solution would be a plus b cos 5t plus c times sine 5t. And if you had a right-hand side that looked like this, e to the minus t minus 2 sine t plus 3 cosine t, this tells you that you had a root of minus 1, and these two terms together tell you plus or minus I. You don't look at the sine t and say plus or minus I, and then look at the cosine t and say another plus or minus I. Together, they are responsible for the pair plus or minus I. And so you would write down for the template here, a multiple of e to the minus t, multiple of cos, multiple of sine. I'm not going to drag you through all 10 of these examples, but you can see the pitfalls you get into. You have to explain all of this example stuff in order to get the students to begin to understand front to back, back to front. And I was never convinced that any of this thing was successful. It was like talking to the air. Students don't grasp this stuff instantly, and it's all a bunch of words. And even though each of these examples would be explained to the student, it you could see their eyes glaze over as you went through this stuff because it's just not making sense to them. So added to all of the difficulties of getting that material across, there is what I would call the tricky case. This is the case or the subtlety that arises when what I call a latent root hiding in R of t, the right hand side, is also a characteristic root. So suppose the root rho is a characteristic root 2 times, and it's a latent root 3 times. What does that require for the guess template for the particular solution? Well, this part of it, and I'll highlight it. This, okay, I can do that. This part of it would be the guess that you'd write down looking just at the right hand side. The t squared comes because of the characteristic root having multiplicity 2. So in other words, this is the first occurrence of the root. This is because of the second. This is because of the third. This is because of the fourth and fifth. So here's this rule. Again, it's words increased by the multiplicity of the characteristic root. The powers on the t's that the latent roots dictate. And altogether, I would say this was not my happiest experience because the students can't absorb this backward thinking without doing enough forward thinking or enough forward proceeding examples so that they get into their heads the pattern that they can abstract from to go backwards. So, what did I learn as an undergraduate out of Rainville's text? Well, what was the text? It was Elementary Differential Equations by Earl Rainville. I had the 1958 or third edition. I presently have a copy of the 1964 second printing of that book. Same, just a second printing, but it goes back to 1958. 58 is the year I graduated from high school. I was in college learning differential equations before that 64 second printing came out. I picked that second printing up along the way. Okay, so what did I learn in Rainville? So here is an extraction from Rainville's text. I copied it and pasted it in here so that I wouldn't have to be going back and forth to alternate files and so forth. So, section 46, method of undetermined coefficients. So he looks at the differential equation. Operator on y is a right-hand side. Well, this is notation he's developed, so it's not that hard to read. Now he calls what I call characteristic equation, he calls auxiliary equation. These are the what I call the characteristic roots. And the general solution of this equation, one, is going to be the characteristic part and the particular part. The characteristic part comes from these values m. And the particular part is he's going to explain now how to get it. So he looks at the right hand side and he says, is itself a particular solution of some homogeneous linear differential equation with constant coefficients, and he calls that operator g. So g is a polynomial in the differential operator d by dx, or d by, here it'd be d by dx. Applied to r gives 0, so g is an annihilating operator. And it has an auxiliary equation, or a characteristic equation, with roots, and he calls them m prime. These are what I call the latent roots, the roots hiding in the right-hand side. So he says, recall that the values of m prime in 5 can be obtained by inspection from r of x. Yeah, if you've got enough experience going from front to back, yeah, you can extract that by inspection. And then he points out that if you apply that annihilating operator to this differential equation, the right-hand side gets hit with that annihilating operator, and it will be 0 on the right-hand side. So if you would now get all the characteristic roots, and he calls them auxiliary, if you get all the characteristic roots from this equation, you're going to have both the m's from here and the m primes from here. So the complete general solution of the right hand that the right hand side signifies or points to, of which that right hand side is a fraction, a fragment, it has to be constructed from all these roots, m and m prime roots. Now, there's more to this chapter 9, because what we showed here is this is section 46, but what's the rest of this chapter 9 that this sits in? So what else is there in chapter 9 we don't know about at this moment? Here's chapter 9, called Non-Homogeneous Equations, Undetermined Coefficients. So this chapter 9 is going to be devoted to learning about undetermined coefficients. We just saw a page from section 46, Method of Undetermined Coefficients. That's what we just looked at. But look at what he starts with. Construction of a homogeneous equation from a specified solution. That's the essence of this backward thinking students have to absorb in order to get going with undetermined coefficients. It puts that first. Well, here, the solution of the non-homogeneous equation, that, once you've got this part structured, then you have the non-homogeneous solution is the sum of the homogeneous solution and the particular solution. Okay, but this is nothing but examples going forward. There's no algorithm that you can apply. It is really just from the intuition you develop by solving a bunch of these non-homogeneous equations, or even from homogeneous equations, that you see what the characteristic roots are and what the solution looks like. There's no magic bullet that I can think of and have been able to think of for algorithmically looking at a right hand side and saying, oh, yeah, the annihilating operator is. So eventually, I was able to cobble together a tool in Maple that allowed me to go through an undetermined coefficients problem according to the thinking that I absorbed from studying Rainville. Now, I've got a differential equation that's non-homogeneous, constant coefficient, non-homogeneous. I happen to pick this one. Now, behind this initialize button is a bunch of code. So I have a bunch of procedures that get called in those steps below. Right here is some pattern matching to determine what does that right-hand side look like. And right in here, I'm constructing from those patterns the appropriate part of the annihilating operator. So let's see. Let's just run through this example. Click this button. I've got the characteristic roots of the homogeneous differential equation. This is a perfect square. Roots are 1, 1. And what are the roots hiding in here? What are the latent roots? 1, 1, 1. So I've got a reproduction of the tricky case. So what would the template for the particular solution be? You've got e to the t, e to the t, e to the t. There's constant C1, C2, C3. And there is a t squared applied to the sum that you would get from these three roots. This would have a t, but there's a t squared multiplying, so it's t cubed. And here you're going to get a t squared times a t squared, and you have t fourth. So what is the annihilating operator for this problem? For some reason or other, this prints out twice. This happens to be the annihilating operator. And how you come up with this is not really necessary for the solving of the problem. It's visualizing the theory that this comes from. Now apply that operator to the given differential equation. So the left-hand side is now going to be a fifth order equation, but the right-hand side is 0. So what's the characteristic equation for this equation? Well, again, it's printed out twice. It happens to factor lambda minus 1 to the fifth. 1 is a root 5 times. Now, if you were to solve that characteristic equation for the characteristic roots, you would get 5 1s. From that, you would have a new fundamental set. It would start with e to the t. There would be an e to the t in every term, and here you pick up t to the first power. See, this is the t to the 0 power, t to the first power, t to the second power, third power, fourth power. Fundamental set for the original homogeneous ODE. Extract from that larger fundamental set, this one. This smaller set. So it's e to t, e to t, e to t, t squared, t cubed, t fourth. That gives you the template for y particular. And there's the template for y particular. We're going to do a little bit forward thinking before we do this backward thinking. Let's take linear constant coefficient homogeneous ODE. Solve it by making the exponential guess. So you get the characteristic equation. Suppose the characteristic equation were this: m squared plus 4m plus 13 equals 0. Characteristic roots would be, using the quadratic formula, 4 plus or minus, you get a 16 minus 4 times 13 over 2. This is 36 minus, so the I comes out, 6, 4 divided by 2, 2 plus or minus 3i. Okay? And we would conclude, or we teach our students, that the fundamental set therefore contains e to the 2t cos t, e to the 2t sine 3t. Because this represents two solutions, right? M squared, you're going to get two solutions. These are the two solutions. All right, so now, in general, depending on the multiplicity of that complex number, u plus or minus iv, which is really two complex numbers, the fundamental set would contain terms of the form, well, here's e to the real part, that's this here, and from the iv part, it could be a cosine, it could be a sine, and we make provision for cosine vt plus some number. And here's the multiplicity factor, t to the b. All right, how do we get these terms? Well, e to one of these complex numbers, let's say plus iv, you'd get this y1. It's a complex solution. And you take minus iv, you would get this solution. And then by arithmetic superposition, really, you add these two solutions and divide by 2, cosine. You subtract these two solutions and divide by 2i, and you get sine. So that's why you don't write down these two complex solutions. You write down these two real solutions as members of the fundamental set. Now, Maple has this command for converting a sum, a cosine vt plus b sine vt, which is possible to have in the right-hand side. Convert it using this into the phase amp form, and this is the phase amp, phase amp form. So you could have this, and it would have a single coefficient. So you look at that and you say, well, everything is coming from e to the lambda t. Would it be possible to search for this form on the right-hand side and have one general annihilating operator that corresponds? So you try that. And so I showed there patterns for each kind of term that might show up on the right-hand side. And here's a constant, and you've got to declare it to be a real constant, times t to the b. And this real constant applies to the exponent b, times an exponential. This is the real part, right? C is the real part. Cosine d, it's going to be a real constant, times t. And maybe you've shifted things into this phase amp form. Unfortunately, pattern matching in Maple is not strong enough to do the job. I mean, just take the simplest term, t squared, pattern match it against here. You would expect, or you would hope, A would come out to be 1, B would come out to be 2, C would come out to be 0, D would come out to be 0, E would come out to be 0. And what happens? Maple says, I can't match this pattern. So that's why I had to break it down into a collection of patterns and write an annihilator for each pattern that Maple found. Consequently, I broke the problem down into a collection of 12 possible forms on the right hand side and the corresponding annihilator for that form. If you have a constant, the annihilator, and I will be using this dt, and you will see why I use a dt momentarily. There is a collection of tools in the DE tools package that deal with construction of operators, differential operators, and they use the notation dt. It could be dx if you're working with x. Here I've been working with t. So if the member term is a multiple of t to the b, the operator would be raised to the b plus 1 power. Because remember, the first occurrence is b is 0. Second occurrence 1. So you've got to upgrade by 1. E to the ct. This is the operator that would annihilate this term. Cos, dt plus constant. Well, it's d minus di times d plus di, which if you simplify is dt squared plus d squared. If you have a t to the b in front of e to the ct, it's this operator raised to the b plus 1. If you have a t in front of the cosine, t to the b, you're going to get what you had here raised to the b plus 1. If there's an e to the ct in front of this cosine, you're going to get d minus this c plus di, d minus c minus di, which turns out to give you this operator, d squared minus 2c dt, which is the first derivative, and a constant. If there's a t to the b in front of this stuff, then you take all of that stuff and you raise it to the b plus 1. If it's just a sine, it's going to look like what you did for a cosine. And if there's a t times a sine, it's going to look like what you did for t times a cosine. If there's an e times a sine, it's going to be just like what you did for e times a cosine. And if this is a tc times a sine, a t times e to the ct times a sine, it's going to look like what you did for the cosine. And there's one other thing that I'll point out here. The multiplicity, the characteristic root, is b, can't be symbolic. So take the simplest form of the operator where you have a repeated root. If you have b plus 1 and you apply this diff hop to de, get an error message, unable to compute the coefficient. But if that's numeric, if that's 2 plus 1 is 3, then it works. So what you discover is that the code that I wrote in that tool that I produced is not really robust. I am not a good programmer. MapleSoft did not hire me for my programming skills. My approach to coding is best described by my experience as a kid growing up in the mean streets of Brooklyn, New York. To me, coding is a street fight. In a street fight, knock your opponent down, then run like hell. Get out of there. Don't stand around to make the event pretty. So I write code, I get it to work, and I don't make it pretty. I just get out of there. I said, I've done what I wanted to do. It's done. So my code is not really tremendously robust. And one of the evidences that it's not robust Let's go back and take a look at that. One of the evidences that it's not robust is this only works with the independent variable t. And the reason for that is I had to ask for help in creating code that would write this stuff down. I asked my supervisor, who I used to talk to once a week, who was the present CEO, Laurent Bernardin. I told him what I was trying to do and didn't know how to do it. He wrote the code for me, and it only works with T. And I never went back and said, oh, this has to become more robust. We have to make it work for any independent variable. Okay, the code's not robust. I showed you how you could read it and see what I did. And the challenge to any participant here, any listener, is if you know of a formula that would take as input a right hand side and output the appropriate annihilating operator, let me know because I've never found it.